Okay, the last aspect of, well, actually there's one more, but the last combination of arithmetic work, that is calculations in vectors. Given two vectors, v, again, I could use the I and the j component form, or I like components much better. And if I choose vector w to be m and n, well, if I add the two vectors, you simply add the I to the I and the j to the j, or simply just the j components and the I components. And if you subtract, you do the same thing in the same order. And if you multiply a vector by a scalar means a constant, right? That's simply multiplying each component by c, right? So scalar is a fancy word for constant. And be careful with vectors. Constant doesn't always necessarily mean what we know. It's equivalent to a constant. It does the same thing. So if I find the magnitude of a vector, r to us is fixed. It's a constant. But the magnitude of a vector, even though it's a scalar, which is the equivalent, kind of like a constant, because it has units. We're not going to get into that right now for this class. It doesn't really, you're learning how to do all of these applications. When you get to physics or engineering and you apply those, then you have to worry about that a lot more. For now, we'll just write the units and go from there. So if I pick a couple of problems, if I look at the next set of problems, in which I'm given those two vectors, I'm going to write those using components. I prefer components way more, but that's only my preference, nothing more. If I would like to find the following, well, that's a really good problem to jump straight into because it requires many things. One, it's asking for 3v. So we're no longer doing this graphically like we did last time. Now we're using algebra. This is simply going to be 3 times, and v is 3 negative 5. So this by itself is 9 negative 15 minus, okay, my components are starting to be less and less components, minus 2 times negative 2, 3, and that would be, either you distribute the whole negative n and make that a positive and say that's a 4 negative 6, or leave the negative up front and just distribute the 2. It makes no difference. And either way, I should get 9 plus 4 and negative 15 minus 6. I should get 13 and negative 21 for my answer. Now, when you get more comfortable with this, you'll start really doing that right here. Not that it matters. It's fine. You can do that in any order you like. And if I look at the next problem, there is a slight difference. Let me see. I was trying to do 46 and 48. Very good. Excellent problems to do to demonstrate the difference between those so you don't get mixed up. You apply order of operations, and the order of operations on magnitude applies identical to order of operations on parentheses, exponents, addition or subtraction, left to right, multiplication or division, all of these things. I think I said that's wrong. One more time. Order of operations applies to parentheses. And if you remember, absolute value, when you did back in the days, ages ago, that fell under parentheses. And what do you do with parentheses? You simplify the inside of the absolute value first, or the inside of the parentheses first. So this is the magnitude of v plus w. What is v plus w? What is 3 negative 5 plus negative 2, 3? Now, you'll notice it's better to use I and j if you're adding and subtracting those to see how they combine, but you'll get the hang of this. That's a 1, and that's a negative 2. Do we all see that? And now I want the magnitude of that. Well, hey, do you remember how that works? If I moved 1 unit to the right and 2 units down, do you remember how to find r? Isn't that the square root of 1 squared plus a negative 2 squared? that would be a square root of 5. And there it is. And do not mix this up. Do not mix that up with the magnitude of v independently from the magnitude of w independently added. Those are not the same. That's a common mistake few students do. Not us, because you know, we are MPath students and we know what's up. So if I looked at v individually, again, nothing new. If I moved 3 to the right, 5 down, what's r? Isn't r squared equal 9 plus 25 or 3, 4? So the magnitude of v would be the square root of that, right? Or I could simply just say the magnitude, okay, a double or a single makes no difference. I could say that's 3, 4, 5, no big deal. You know what, something's not right. Oh boy, I messed up somewhere. Let me go back and adjust a bit. Yeah, that's not 3, 4, 5. There's v. So if I take the magnitude of v, look at that. See what happened when you rush? No rush. That is 3 squared plus negative 5 squared. Magnitude of v is the square root of 9 plus 25. That's 34. There. Wow. And what's the magnitude of w? Well, magnitude of w if I do the same, if I go to w and say that's negative 2, 3 up, wouldn't that right there be the square root of 9 plus 4? So this is the square root of 9 plus 4. That would be radical 13. And since I'm taking the sum of those, that would be the sum. And notice, this right here, nowhere is close to that. So the magnitude of v plus w is not the magnitude of v plus the magnitude of v w independently. Those are not the same. Do not make that mistake. Now, one last thing that I have to set up before we actually move on to the applications, which is the most fun part, and that is a unit vector. A unit circle is a circle with a radius of 1. A unit vector is a vector with a length, a magnitude of 1. How do you force anything in math, do you think, to have a length of 1? You divide it by its length. Does that make sense? Any quantity in math, other than 0, of course, you divide it by its length, guess what you get? You get a magnitude of 1, a length of 1. So, if I was given a vector in general, if I was given a vector v, if you happen to be a unit vector in the direction of v, I'll talk about that in a minute, then you would be take any vector divided by its magnitude, right? Again, recall, whether you say this or this, to us that's the same thing. Some books use this, some books use that. We're going to use this back and forth. In calculus, they use this notation. In physics, they use that. We're not going to disagree. They're both called the magnitude. So let me show you what this means, and this is a big deal. If I would like to look at number 49 through 54, directions, find the unit vector in the same direction as v. Direction is extremely important. I'm going to start with a simple example, a very simple example. 50. Remember, graphing is half of it. If we can graph r and theta, if we can graph the modulus and the argument, we could sketch a graph of v and visualize where this is. And notice, this is really 0, negative 3. That's like me saying, don't move in the x, 1, 2, 3 down. This vector is right there. If I want to find a unit vector in the same direction as v, well, wouldn't you just move 1 unit down? Wouldn't you say 0, negative 1? That is a vector that's pointing in the same direction as v, but has a length of 1. That doesn't look pretty. pretty. I want this to look a bit nicer. Let me make that a bit nicer. So V is, let me center that, minus 12. We have plenty of space. So V is 1, 2, 3. There's V right there. I don't know why I keep on writing too small. If I want a vector pointing in the same direction, but with a length of 1, hey, isn't that it right there? We call that vector U. Now, I don't like the fact that they use U for unit and U for something else, but we'll play along. Now, what if you didn't know that? Well, what is the magnitude of vector V? If I just want to use the formula, isn't that the square root of 0 squared plus a negative 3 squared? Wouldn't that be just the square root of 9, which is 3? Remember, you can't have plus or minus in vector land. And didn't we go by the formula and said U is actually whatever V is divided by its magnitude? Well, what is V? V is 0, negative 3 divided by, so we multiply by 1/3, and we know how to multiply by a scalar. Wouldn't that be 0, negative 1? And there it is. So if I use the formula for something that I could see, hopefully the formula makes more sense. I don't need the formula for a problem like this, but I would need it for other problems. I'd like to look at another problem. Let's say we're looking at something like 54. So here, if I really glance at this graphically, well, I know how that goes. I am going to move 2 units to the right and 1 unit down. So here's that vector. Well, if I take the magnitude of V, that would be the square root of, well, that's nothing more than this is 2 and this is negative 1. That's like our R, right? That's the square root of 5. Are we getting this? And I'll say U is 1 over radical 5 times 2 negative 1. You could leave it like that. I don't mind. That's the same thing. Or you could say 2 over radical 5 and negative 1 over radical 5. And if I go component form, 2 over radical 5 and negative 1 over radical 5, that vector right there possesses the same direction as the original, but it has a length of 1. Pretty cool, huh? And you need that for a lot of applications in calculus, physics, other classes. The next problem, number 59 through 64, it says, write the vector in the form AB, given the magnitude and the angle. So if they gave me R and theta, can I find X and Y? Well, yeah, of course. You could graph it. You don't have to. But I'm graphing that just so you could see it. Look what happened. They rotated 45 degrees and they moved 8 units. Can you tell me what the A component and what the B component is? Well, hey, isn't this taking the place of X? This is 45 degrees and this is B. Wouldn't that mean the A component is actually R times the cosine of theta, loosely speaking, or the magnitude of V times the cosine of 45 degrees? That is 8. And what's the cosine of 45 degrees? Radical 2 over 2. So this is 4 radical 2. And if I look at B, or the J component, that's like, again, loosely speaking, that's R times the sine of theta. That's magnitude of V times the sine of 45 degrees. And that is 8 times radical 2 over 2, and that is 4 radical 2. And guess what? If you move 4 radical 2 to the right, 4 radical 2 up, you will be at that location again, and there it is. And that's pretty much how this works all the time, right? I could derive it. If you want to figure out A, there's an angle, there's the hypotenuse, cosine of 45 degrees equals the I component divided by A, and if you cross multiply, you'll get A to equal 8 times the cosine of 45 degrees. But we already know this.